Traditional wind turbines look like pinnacles of green technology, but to an engineer, they're leaking power, leaving a massive trail of wasted wind energy in their wake. As wind passes through a turbine, the spinning blades force the air behind them to swirl in the opposite direction. This swirling wake is a vortex of wasted rotational energy. Single-rotor turbines only capture the linear force of the wind, letting the rotational energy dissipate unused into the sky, leaving a significant amount of power behind. Engineers solved this by designing the dual-rotor wind turbine. By placing a second set of blades on the same shaft, they can squeeze the remaining energy out of the weight. These two co-axial rotors spin in opposite directions. The front rotor spins clockwise, while the rear rotor spins counterclockwise, catching and straightening the swirling wave. Imagine trying to wring out a soaking wet towel using only one hand while holding the other end still. You will squeeze out some water, but much of it remains trapped inside. If you twist both hands in opposite directions at the same time, you wring out every last drop. The two contra-rotating rotors act like those two twisting hands, extracting maximum energy. By catching the swirling wave and straightening the flow, the rear blades convert what would have been lost weight turbulence into additional, clean electricity. Think of a speedboat racing across a lake, leaving a chaotic frothing wake of water behind it. That wake represents wasted energy churned up by the propeller. If you added a second propeller spinning in reverse behind the first, it would catch that swirling water, flattening the wake while recovering energy to push the boat faster. Standard wind turbines are governed by the Betz Limit, a mathematical rule stating that a single rotor can only capture 59.3% of the wind's energy. If you add too many blades to a single rotor to catch more wind, you create too much drag. The air backs up like a solid wall and spills around the edges, reducing output. Imagine trying to catch tennis balls with an extremely fine mesh net. The balls will hit the net and bounce off the front, blocking other balls behind them from getting through. If you make the mesh openings very wide, the balls will slip through the gaps untouched. The net fails to capture their energy, much like a turbine with too few blades. The solution is using two nets in a row. The first catches some balls, and the second catches the rest. In wind energy, this dual-rotor design is governed by the Newman Limit. Double rotors also solve structural problems. If you squeeze the trigger on a powerful drill, the motor exerts a twist or torque that tries to rotate your wrist. If you welded two drills together spinning in opposite directions, their twisting forces would cancel out. This torque cancellation is used to stabilize wind turbines. By canceling out the torque forces at the top of the tower, the contra-rotating rotors protect the structural steel from twisting stresses, extending the turbine's lifespan. However, double rotors face a challenge: dirty air. It is like driving a car closely behind a semi-truck on the highway, where the turbulent weight buffets and shakes your vehicle. Because the rear blades sit in the turbulent wake of the front rotor, they endure constant buffeting. This high cycle fatigue requires advanced materials to prevent structural cracks. Specialized gearboxes are also required. To drive a single generator from two contra-rotating rotors, engineers must use nested concentric shafts that rotate inside one another. This complexity increases construction costs, adding a premium of usual $100, $0 to usual $150, $0 per turbine compared to standard single-rotor designs. But this investment pays off. By squeezing energy from the wake, dual-rotor systems can boost annual energy production by up to 40%. This extra power dramatically reduces the levelized cost of energy over the turbine's lifespan, recovering the hardware premium within a few years of operation. This is crucial as wind turbines grow. Single blades are now longer than football fields. Transporting them on trucks through narrow highway turns is becoming logistically impossible. It is like lifting a heavy beam with two synchronized cranes instead of building a single colossal crane. Using two smaller components simplifies the entire construction process. Dual rotors allow turbines to match the power of a giant single blade using two smaller, easily transportable blades, bypassing the logistics bottlenecks of onshore wind farms. As we expand green grids, dual-rotor turbines offer way forward, squeezing every drop of energy from the wing while keeping transport logistics manageable. At Layman's Field, we believe that understanding the future of energy shouldn't require a degree. We break down the engineering behind these breakthroughs in simple terms. By wringing out the wasted wind, dual rotors are rewriting the physics of clean energy. Thank you for watching Layman's Field. We hope to keep bringing knowledge for everyone.